So far we saw what happens when we sample an analog signal, but now what happens if we further downsample an already discrete signal x of n to reduce its sampling rate. So downsampling by n means that we only keep every nth sample and we discard every sample in between. So observe that this results in a normalized frequency which is a factor of n higher. So this downsampling process can also be seen as first multiplying the signal with a sequence of unit pulses, so it's a 1 at each sample position and zeros in between, and later dropping the zeros. So this multiplication with the unit pulse train can now be used to mathematically analyze downsampling and looking at the resulting spectrum, first including still the zero. So the frequency response now becomes this equation here. So for m, all integers m. So what we can write down downsampling as the multiplication of the signal with a sampling function. So in the continuous time it was this sequence of Dirac impulses, but here is a sequence of unit pulses at position multiples of n. So this is the sequence of unit pulses is equal to 1 if n equals to m times n, or 0 elsewhere. So the sampled signal with the zeros still in it becomes this x of n times this sequence of unit pulses. So we will do the same what we did before, but now we will replace this x of n by x of n times the sequence of unit pulses. And this, so far this is an intermediate signal because it's still there are the zeros there, and the zeros will get removed before transmission or storage to reduce the needed data rate. The decoder upsamples it by reinserting the zeros to obtain the original sampling rate. So observe that this is then also the signal that we obtain after this upsampling in the decoder. So hence the signal looks interesting to us because it appears in the encoder and also in the decoder. So what does its spectrum or frequency response looks like? So we saw that the downsampled signal x of t can be written as the multiplication of the original signal with the unit pulse train delta n. So in the spectrum, on the frequency domain, this becomes a convolution with their Fourier transforms. So first, the Fourier transforms of the unit pulse train is a Dirac impulse train. But this is not easy to derive, so here we will apply a trick to make it mathematically more easy and to get converging sums. This is not something I really enjoy doing. It's a trick that you need. First you have a guess, and then you try to prove that your guess is correct, but you need a lot of experience and intuition to have a good guess. So let's have a guess about what the Fourier transform of the unit pulse train is. So we get Dirac impulses at frequencies of 2 pi divided by capital N times k. So the fundamental frequency is 2 pi divided by capital N and its harmonics. So the fundamental angular frequency is 2 times pi divided by capital N, because our original sampling frequency was 2 pi, and now we reduced it by a factor of n. So with a constant factor that becomes clear later, we get our guess to this equation here. So this delta 2 pi m n capital omega is guessed to be the Fourier transform of the unit impulse train, so the direct impulse train. So what we need to do, we need to verify it. So the inverse discrete time Fourier transform is given by this equation here. So from here we go to here, and we have that this is the inverse discrete time Fourier transform. So now we have to prove that this is indeed our unit pulse train. So to do that, we will look at this sum, and we see that this is a geometric sum. So it's a sum over a constant with the summation index in the exponent. So let's remember the geometric sum. So if we have the summation, we have an exponential going from k equals to 0 to n minus 1. So what we can do is that we can check what happens when k goes from 1 to n instead from 0 to n minus 1, and then we get this is the s times c. So we have this here. Now if we take s times c minus s, so this is the summation, we'll get that s times c minus s is equal to c to the power of n minus 1, and then if we want to find this s, we will divide this. So s here is like s, and then c minus 1, we put s in evidence, and then we get this thing here. And if we replace the c by this e to the power of j 2 pi n times n, we will get this sum here, and that can be computed in a closed form. So we're replacing c by what we had, and we have this equation here. So in order to get our unit pulse train, this sum must become capital N for n equals to m times n. So how can we check this? We can simply plug this into the sum. So the right part of the sum is undefined in this case, but we get an easy result by looking at the left hand side. So we have that this part here is equal to 1, and this sum becomes n as desired. Yeah, but for n is different than m times n, we need the sum to be 0. So we can now look at the right hand of the equation, and the denominator is not 0, and the numerator becomes 0 when n is different from m times n, and hence we have that this sum is indeed 0 as needed. So this proves that our assumption was right, and we have that the sequence of pulse is given by this equation here. Yeah? And now we can use this expression for the unit pulse train in the time domain, and then we can compute the Fourier transform.